So this is the next chapter in the statistics textbook, and it's a little out of order how I usually teach this course. So it's going to be interesting to see how it works for you folks. I think it'll actually be okay. So about significance testing tends to be a hard topic for people. I'm hoping that the work you did with sampling distributions this last week will help you out. And the question we're trying to answer is what does it mean if we get a sample and then it's seems to be there's a really small probability of it happening? I mean, does that mean it's different from what was stated? And that's what it's meant by statistical significance. One thing you should probably do before you finish watching this video, and I talked about it in the week 6 work, is go watch that Against All Odds video. It's a short little 10-13 minute clip. They do a nice job with the overall picture so go check that out and then come back and watch this. So here's our first problem, and this is actually very similar to what we did last week. Some researchers claiming that the average age of woman when she gives birth to her first child is actually higher than it was back in 1990. So she obtained a random sample of 40 women, and for that 40 women, that average age of first birth was 27.1 years. Now this is referring to the population standard deviation. Usually we don't know that, but we're going to treat it this way, and this will let us use z-scores like we did last week. So what's the sample size? Well, 40 women. And then as you hopefully remember from last week, the way you describe these sampling distributions, well, they're normal. The central limit theorem tells us they're normal. They tell us that the center is that stated average, and the variation or the spread is described by a standard deviation because it is normal. It's a symmetric distribution, and the way we get that standard deviation for these sampling distributions is take the old standard deviation for the entire population and divide it by the square root of the sample size, because as we learned last week, as that sample size gets larger and larger and larger, there's less variation in how those means will fall around the true mean. Those sample means will fall around the true mean. So for this situation, the standard deviation is 6.4. We're going to divide that by the square root of 40. So that works out to be 6.4 over what is it, 6.3. I did this earlier. Yeah, 6.3246. 6.3246. Honestly, I'm just going to let the calculator carry all the decimal places. So I'll divide that, and I got a standard deviation for my samples of size 40 of 1.0119. So that's our standard deviation. Some textbooks will use this notation for that, where it's the population standard deviation for all those different X bars. Don't get hung up with the standard deviation, the notation. Remember, we're looking for a standard deviation for a sampling distribution. That's all you need to remember when we're dealing with sample means. So we've got the shape, the spread, the center. Now we're going to say, so what about this sample of 27.1 years? She's thinking that is actually higher than the old average of 26.4. Well, it is higher, but then we got to remember about sampling distributions is as you take repeated samples, you won't necessarily get the stated center, but it'll vary in a normal distribution around that old center. And then our job becomes, is it far enough away from the old center to say it's an unusual event? And that's where we're going to go next. So what we're really doing is we're looking for this area right there. The probability that of getting a sample that far away from the middle or larger. So using that normal curve applet, I set the mean, so that's the mean, right? That was the middle. And there's the standard deviation. Notice how it marked out the nice plus or minus 1, 2, and 3 standard deviations. And it gave me that area of having us getting a sample of 40 women with that high an average or more. Now, there's a 24% chance of doing it if we make that a percentage, right? It's a 24% chance of getting a sample of 40 women with that high an average or higher. And that's not a rare event, right? If you think back to how we talked about two z-scores, if a value was more than two z-scores away from the mean, then it was unusual. Well, certainly two z-scores would be way up here, so this is not an unusual situation to have occur. So we couldn't say that. So the researchers said that they felt that the average age had increased. Well, looking at this result, we couldn't. The data doesn't support that conclusion. So what we did is we ran a significance test, and what we should probably do is formalize this. And then we got to talk about this situation. I mean, I use z-scores for this, and what lets me use z-scores is saying that, hey, the population standard deviation was that 6.4 number, and usually we don't know the population standard deviation, so we're going to change things up a little bit. So let's formalize this process. So what I'm going to try to do with this next set of slides is walk you through this. We've already done all the work. We're just going to formalize it, and these are the items that you need to include when you conduct a significance test, whether it's about proportions or means or two samples or whatever we're going to do. Okay, it's always the same format, which is kind of nice. The first step is to write a claim. It helps you put it in context. So the claim the researcher is making is that the average age of a woman before she has her first child is greater than the 1990 average. Okay, so he's trying to think so she thinks it's increased. Now, some things to remember that this textbook we're using this semester talks about what's your random variable. Well, the random variable is the average age of women before, and I didn't write that in symbols, but I should add, she has her first child. So the age of first birth for these mothers is the parameter, and the claim is that we think it's increased. Okay, and what's the random variable? Well, the random variable is the average of 40 women. Okay, not a single woman, but the average of the sample of 40. Okay. So the next step is to write, well, what are you testing? What are the hypotheses? Well, there's two situations. It could be that the researcher's wrong. We already know she is. And that the average age hasn't increased. It's exactly the same as it was back in 1990. I mean, it's possible it might have decreased, but we won't worry about that, okay? We're just concerned about has it changed since then? Has it increased since then? And then our HA, our alternative hypotheses, is, now this symbol is a mu. If you try to find it in text, it looks a little more like a U with tails, but this means the population average. So the population mean. Okay, we think that parameter has changed what her claim is. Okay, and I said greater than to show that it has increased. Okay, and some buzzwords which you can think of, because this is a textbook kind of question. You see where it says is greater than? That tells me that's going to be a greater than symbol there. And this is called a right-tailed test. And it's right-tailed because I'm dealing with greater than. Okay, so we've got, and I like to say, oh, the claim is going to be my HA. Sometimes you claim as your HO. It depends on the problem. So our test statistic is a z-score in this case, because we know that population standard deviation, right? They told us that right there. That's a population standard deviation. So I calculated my z-score, and if you remember back from a couple weeks ago, a z-score is our x minus our mean divided by the standard deviation. Now, remember, the standard deviation is not the 6.4, but it's the one that came from 6.4 divided by the square root of 40. Okay, because we're in that sampling distribution mode. And to do that calculation, so I came up with a z-score of 0.692. So that's my test statistic. Now the p-value is just the probability of getting a test result that high or higher. And you already have seen this, that I just used that z-score normal curve applet. And that's the probability of getting a sample that far away from the mean or higher, which is a pretty high p-value. So how do we make a decision? Well, you see, I already wrote we can't reject HO. How did I make that decision? Well, if you think back to don't think back, but if you take a look back at that first slide when we did this, it says you test at the 5% level of significance. So what the level of significance is, it's the ruler that we can use to make our decision. So we've got the mean, right? We know that mean of 26.4, and HO says no, your sample is not that far away from the 26.4 value. That it's just any difference can be explained by random sampling error or random variation from our samples. So I've seen some people do this where they put a happy face above the mean because that's HO can't be rejected. Okay, it's you know, if you get rejected, it's not a good thing. So we put the happy face here to show that HO is happy, and we can't reject it. And then this area over here is, we can think of that as the rejection region, where HO is going to be rejected, that it looks like this sample result is far enough away from 26.4 to say there's something different going on. So what we've got going here, so the level of significance tells us, hey, if this area is less than 5%, we can reject HO. And we know that our p-value was what, 0.2445 or something like that. Well, 0.2445 is not that small. So really what's happening is, and if you think about that graph, right, that the applet generated for us, that was something like, you know, it was way over here, and this area here was the 0.24. So you see how that's not in that rejection region. This test result is still in the place where we can't reject HO. It's not a rare enough event to say or unusual enough to say that this sample is a very strange sample if we're comparing it to the 26.4. It's perfectly explained by sampling variation. Okay, so take a look at your level of significance, take a look at your p-value. If your p-value is smaller than your level of significance, we reject HO. Think of this as a limbo bar. If you've ever done the limbo dance, 0.05 is our limbo bar, and this level is too high. I can't get under the limbo bar, so I can't reject HO. I can't get away from it. Chart, and I'll have a copy of this in the week 6 work area. This came from another textbook that I use, and I really like it, that I'm willing to break copyright laws to give it to you. But since it's in a course, that's okay. So what we're going to do is, this is in order to help you word your decision correctly. We know we can't reject HO. Okay, so does my original claim contain the condition of equality? Remember how when I said, back when I first started setting this up, the claim was HA. So the claim did not have an equality. In other words, it wasn't that it was equal to 26.4, it was greater than. So our claim was not the condition of equality, so we're going to go down this path. And did we reject HO? No, we didn't. So how I'm going to start my phrasing is I'm going to say there's not sufficient sample evidence to support the claim that, and then remember how we said the claim was that the average age of women before she has her first child was greater than the 1990 average. So that's exactly how we'd word it. We'd start, there's not sufficient sample evidence to support the claim that the average age of women before she has her first child is greater than the 1990 mean. And then that would make everybody happy, and you put it in context so you sound like you know what you're talking about. Okay? Now, So the author does make a discussion about type 1, type 2 errors. She also talks about the power of a test. You do not have to worry about power of a test. I'm not going to test you on it. It's an advanced topic we don't need to cover. But it's good to understand what a type 1, type 2 error is. And so in a nutshell, if I know that like for that last problem was about women's average age of first childbirth has increased, if we said, no, that hasn't increased. So what we could have been making, I mean, we're probably right, but what we could have been, the error we could have been making is a type 2 error, because we were saying we failed to reject the null hypothesis. We said, hey, we can't reject HO. The average age hasn't increased, but what if it actually had increased? And we don't know that. I mean, that's the risk we're doing in running this test. You never know anything exactly. Just gotta make a range and make a guess how certain you are. So that's a type. We could be making a type 2 error if we had gone ahead and said, if we had rejected HO, and we shouldn't have. That would have been a type 1 error. And what I've got is I've pulled some problems, some other exercises that might help us look at some of these. So this came from another textbook I use, and we're supposed to identify whether this is a type 1 or type 2. These are type 1 or type 2 error. Now, this deals with proportions, and I'm going to do that in a minute, but not right this second. It's okay. Just remember, here's HO, here's H1, HA. So a bank wants to see if enrollment in their website is above 30%. So HO is, no, it hasn't. It isn't above 30%. It doesn't say what they're saying, but just that it isn't 30%. And HA says it is above 30%. It's actually higher than what they think. And they're saying, okay, so they reject the null hypothesis. So we're saying we're going to reject this. It looks like it has changed. Later, the bank finds out the actual enrollment is only 28%. So is this a type 1 error where they're rejecting HO when they shouldn't have? We're saying it's above. They said we're rejecting HO, which means the actual average is above 30%. Later they found out that it's only 28%. It's not above 30%. So to see how HO is true, well, it is. But we rejected it, so that's a type 1 error. So then let's see. A student tests 100 students to determine whether they prefer Coke or Pepsi, and finds no evidence that the preference for Coke is not 0.5. So later it tests all students and finds no difference. That's worded like a lot of double negatives. No evidence that the preference for Coke is not 0.5. So one of our options is no. So what's happening here is the student is saying, let's see, HO, that the percentage of people who like Coke is 0.5, and what they're trying to test is that it's not 0.5. So we're going to do a two-tailed test. And they're saying they found no evidence. And then the marketing company also found no evidence. So the student didn't reject HO. Failed to reject HO, and it looks like that's actually true. That's the true thing. We failed. Failed to reject HO. The null hypothesis is true. That's a correct decision. It wasn't a type 2 error, or a type 1 error for that matter. Okay, so you see how that one worked? That was a little confusing. Made me think about it for a minute. And a pharmaceutical company tests whether a drug lifts headache relief rate from 25%. Achieved. So does the drug work better than the placebo? And the test shows that it doesn't because the p-value is pretty large. So let's just stop right there. So with that larger p-value, the pharmaceutical company is not going to reject HO, right? And then further testing shows it actually does relieve it. So actually, instead of the new drug actually does relieve headaches in 38% of the people compared to the 25. So it looks like HO was false here because it looks like the drug does work better than the placebo. So what are we doing here? So we know the null hypothesis is false because it does work better than the placebo. But we did not reject the null hypothesis, so this is a type 2 error. So for this problem, we're trying to determine, this researcher is trying to determine, he's speculating that artists are more likely to be left-handed than everybody else. So they went out and ran a simple random sample, and we surveyed 150 artists, and 18 of them are left-handed. So, and higher than 10%, right? So they want us to conduct a significance test. Well, one thing we need to check on is some conditions. This is a simple random sample, so we have a random sample. That's good. The other issue that can happen is maybe your sample's not big enough. So one of the stipulations you'll read in the book, it talks about, hey, if I take my 0.1, that's what the general population is, and that's what we think. That's what we think is happening here. Is 0.1 times 150, well, is that bigger than 10? Well, it certainly is. That's actually 15. And then if you take 0.9, 1 minus, or 100 minus 10, or 1 minus 0.1, and multiply that by 150, is that bigger than or equal to 10? Well, it sure is. So that's a large enough sample to say that the central limit theorem is going to take hold and we can use it. Just to check, because this is the textbook, most of the time this is always going to work. And I'll be honest with you, I will never give you that on a test or quiz. I'll never give you that. I'll give you samples at work. Okay? At least certainly for proportions. So let's see. So what are we going to do? So we haven't really talked about sampling distributions for proportions yet. Mr. Nystrom did. If you watch that video about p-hats, piles of p-hats. But what's happening here is that this is the proportion of people that are left-handed. And we could come up with the central limit, we know the central limit theorem holds because we just did this. So we know that the shape of this distribution is normal. We know the center of this distribution is 0.1, 10%. The standard deviation is, well, I'll show you this, but I'm not going to ask you to do this. My open math might, but on a quiz I probably won't. So what you do is you take your sample, your population proportion, which is 0.1, times 1 minus that population proportion, divided by the sample size, then you take the square root of the mess. So for this one, it's going to be 0.1 times 1 minus 0.1 over 150, and then we take the square root. And we could go ahead and calculate that. What I'm going to have you do is, there's many applets that'll do these significance tests for us. So to be able to do this calculation, we're not going to worry so much about that. I do want you to understand, though, that you are using this as the supposed center and not the sample result. One other piece of a symbol that I want you to understand. P stands for the population proportion, or the population percentage, if you write it as a percentage proportion. P hat, and we pronounce that P hat, that's the sample proportion. Notice that we're dealing with categorical variables now. Okay, that's one way we'll do this. And you'll see there's going to be a bar graph that'll pop up later here. So for this sample, we had 150 people, 18 left-handers out of 150 people. So we're going to do 18 as our part, and 150 is our whole. And if we make that a decimal, where's my calculator? Let's see, 18 divided by 150. I should be able to do that in my head. So I'm not. So that gives me about, actually gives me exactly 0.12. So about 12% of the sample were left-handed because he's an artist. And so is that bigger than 10%? It sure is. But now we have to find out if it's statistically significant. And then that's what this whole process of a significance test will answer for us. So p-hat's the sample proportion. And you always do the part over the whole. The bigger number will go on the bottom. That's one way to tell that too. Okay? So as we did before, the claim is, first thing you want to do, what's the parameter of interest? Well, it's the parameter, is it the proportion of artists that are left-handed, and how do they compare to the proportion of left-handed people overall? So here's what the researcher's claiming, so that's what we're going to work around. And then, similar to what we've done with we did with averages, with means, we say that, notice the P, I'm not using p-hat, I'm using P. This is the population proportion for left-handers is equal to 0.1. Artists aren't any different, is what this is saying. And this is the claim that the research is making, that artists are different. They have a higher proportion of left-handers than the general population. So in order to get the test statistic and the p-value, we could do that normal curves thing, applet, but we'd have to calculate the standard deviation. I'll also link this applet in the week 6 work. It does a lot for us, and I'm going to encourage you to use it. Our calculators will too. And if you look in the test, in the textbook, it talks about a 1-prop z-test. I won't go much into showing how to do this. Not all of you have these calculators, but all I pressed was stat, I arrowed over to tests, and for this test I'm going to do a 1-prop z-test. You need to provide the calculator, and this will serve well for the applet we're going to look at too, is you got to tell it what your HO value is, and HA. That's something I haven't talked about. Make sure when you write your HO and H1 you use the same number in each. You don't want to use one value in HO and a different value in H1. You're trying to say, is it different from the center? And then you get to type in how many successes out of how many total. And here I'll type in 18 out of 150. I guess I should have done that. And then you got to say what your HA is. What did you have a greater than, a less than, or a not equal to, a two-tailed test. And then you can calculate it. It'll either, if you have it draw, it'll draw you a normal curve, and it'll tell you the p-value and the test statistic, the z-score. So if you have one, use it. It's pretty slick. It works better than the applet, though the applet works pretty well. So using this Rossman Chance applet, that's the link that I provided for you. There's this drop-down menu here, and we're going to use this often over the next couple of weeks. You want to do the drop-down because this is about a single proportion. You want to do one proportion. That's the default, at least it always has been. And then you're going to type in your N, which was 150, type in their count of left-handers, which was 18, and you can calculate it, and that'll give you the sample proportion. Of course, we knew all that. Then you come over here and make sure that you have the test of significance checked. And then it'll give you HO and HA. It uses the value, the symbol pi. I don't know why they use pi, not p, but that's how they set up. And then you're going to type in, notice this is just what my HO and my H1 are. Notice I used the same number there. I didn't type in the 0.12. I'm going to see how that tests. Then you can click calculate. It's important to click on this and change that to the right tail, whether it's a left tail, right tail, or not equal to a two-tail. And notice it gives me the sketch, the distribution. There's the center, the 0.1, right? And here's the test result, the 0.12. And there's the area, and it gave me the z-score, the test statistic, and there's the p-value for it. So it does it all in one foul swoop. So then we're going to look at the p-value. We're going to compare it to our level of significance. Remember, this has to be smaller than this in order to reject HO. So since it's not, we can't reject HO. This is not a rare event. And then you want to use that flow chart that I gave you earlier in the other one. The sample evidence doesn't support the claim that that the left-handed people and artists are higher. I'm not wording that wrong, but you can read it. Okay? So that's a test of significance for the proportions.